All right, guys, here we go. We're going to graph some logarithmic functions. We're going to make a table of values. We're going to do something very similar to what we did for exponential stuff, but you've never heard of logarithms. So on your calculator, you will notice there is a button here that says log. Now, there's the whole basic unit we're working on. Unit 4 is logarithmic stuff and exponential stuff. So we're just going to scratch a little tiny bit of the surface here today. I want you to be able to graph something that looks like this. Once again, when you have logs, you could have scalars. You could. This is just like base. That's a base value. Okay. So logs have different bases. And you're like, what the heck are you talking about? Well, here we go. Let's just start with the one most common logarithm is this guy. See, this guy right here is called the common log. The most common log that there is when it's got a base of 10. Now, on your calculator, there's that button that says log. Your calculator is programmed to understand what's called logarithm base 10. What does that mean? Well, logs are funky numbers, or funky functions. Funky functions. Okay. You plug numbers into them, you get numbers out of them. You do. But on your calculator, you'll notice they don't have a little tiny 10 right there. Well, your calculator is programmed to understand base 10. Let's just graph one and then I'll kind of clue you in as we go, because actually graphing them is super easy. You just have to plug numbers in and get numbers out. So just like we did before, we're going to be plugging in some numbers. So I'm getting my ruler, make it look pretty and everything. And I'm going to say I'm going to plug in X, I'm going to get out Y, but here's the deal. I'm going to plug in 0.1, 0.5, 1, 2, and 5. Now, when we get to the practice, you'll notice I have this written out. Every time we graph a log function, we use these 5 numbers because they are going to be the easiest. They are the easiest to use, and then you start seeing there's a pattern involved with them. Now, one thing is for definitely, for sure, without a doubt. If you want to find the log of a number, like what is the log of 0.1? This is what it looks like on your calculator. I hit the log button. I go log 0.1. And just, that's what it looks like. I'm going to take the log of 0.1. Well, guess what? My calculator says, yeah, that's the answer, -1. I go, oh. So when I plug in 0.1, I get out -1. Well, wonderful. Okay, so it's input, it's output. That's what we're, how about log of 0.5? Now log, so I hit the log button again. I got to push log. Then I go 0.5, and I'm going to close my parentheses because it just bugs me when I don't. And I'm going to get this magically weird number. -0.301022 or 299957. Okay, when we start solving equations, we're going to need a lot of decimals. But if we're going to graph, we don't. We're going to round every single decimal answer to the nearest tenth. So I'm going to round this one off to -0.3. -0.3. Now, log of 1. The log of 1 is always 0. Bam! It's always 0. The log of 1 is always 0. So true. Forever and ever true. Now, the thing is, your calculator will never lie to you about that log of 1 is 0. But since it's always the same answer, I just write down 0 as soon as I don't even use my calculator for that. Log of, what do I want you to punch in? 2. Now check this out. Log of 2. I told you there's patterns in these. Look at this decimal. Oh, does it look familiar? It does, because it's 0.3. And then log 5. Log 5, because we need one more log number. So here we go, log of 5. Round that thing off to the nearest tenth for me. The log of 5 is 0.7. 0.7. Now, I have a table of values that I generated here. I did. And I'm going to sketch a graph of this stuff. I am. I'm going to show you, though, that when I sketch this graph, I'm using a regular old XY coordinate system, right? But one thing you might have wondered, how come I didn't plug in any negative numbers? How about log of -2? Well, because I can't. It says no, non-real answer. Oh, crap. How about the log of 0? You didn't plug in 0. You plugged in 0 on the other ones. Well, let me get here. Let me see. It says error, log of -2. How about log of 0? What does it say? No, it doesn't like that either. I'm going to quit the screen. I'm going to say second mode. So second quit. And what is it? It's basically, it's an error. It's like we don't like negatives or 0. Well, guess what? Let's go back here. That's why I wanted you to pick a number that's really close to 0. 0.1 is close to 0. You'll get output. 0.5 is really close to 0, but not as close as that. But you'll get output. You can only plug positive numbers into a log function. That's the big thing. So if you can only plug positive numbers in for x, that means everything on this side of the x-axis doesn't matter. All of this stuff doesn't matter. I'm not going to get any output over there. The boundary marker for a log function is right here, the y-axis. Guess what? The y-axis is an asymptote. That's an asymptote for this function. There is a boundary marker there. Hey, guess what? I plugged in a 1, a 2, and a 5. So when I graph these, guess what? I only need 5 dashes on this side to make this graph work. You'll also notice when you do this, you don't need many dashes going up or down. You don't. Let's try the first one. If I plug in 0.1 for x, I get out -1. So if this is 1 unit, 0.1 would be really close to the asymptote. I'd get out -1. So I'm like down here. When I plug in 0.5, that's right here, I'd get out -0.3. When I plug in 1, I get out 0. When I plug in 2, I get out 0.3. When I plug in 5, x is 5, I get out 0.7. So what happens is I connect these dots, right? As I plug in more and more and more x's, this thing will continue to go up. The thing is, it does not rise quickly at all. Logarithmic functions do not grow at a fast rate, but they do grow. That's okay. That's correct. Over here, like I said, this is going to be an asymptote. So when it comes to here, it's like it falls down. It just drops like a rock. So every graph that I draw that's a logarithm is going to have this type of vibe to it. Now, let's take a look, because you're going to check your answers on the calculator. So I'm going to go y equals, and I'm going to say log x. Y equals log x. I like to close the parentheses. It bugs me when I don't. Ready? I'm going to hit graph. Look at that. Now, you can't see the vertical asymptote here. You can't. I have to warn you about your calculator. It does not know how to think. Calculators only spit out what you put into them. So I'm going to give you a heads up. Your calculator, no matter how sophisticated and cool this is, cannot draw a vertical asymptote. When something's about to go vertical, your calculator goes, I don't know how to do that, and it stops. So, be careful. Your calculator will lie to you on occasion because it does not know how to think. It only knows how to spit out numbers. So there's our graph. We can check it, just realize it won't show the vertical part. Now, here's the thing with this. A log is a real weird bird. It's got this base value, right? And that base value can change. That base value can change. I'm going to come back to this picture. I'm going to get it out of my way for a second. And I want you to see this one right here. Log. Well, what's the base now? What base do I have in this one? My base is 7. Well, what's the difference between a log base 7 and the log I just drew? Well, here's the thing. Your calculator does not know how to do anything but base 10. So we have something called the change of base formula. And the change of base formula is really easy. I'm going to hit clear because I'm going to need this in a second. But here's how you trick your calculator into thinking it's a different base. You take whatever the number is you're going to plug in, whatever it is you want to plug in, then you divide it by the log of whatever the base is. So this is going to be log of whatever number I want to plug in divided by log of 7. And I'm going to plug in 0.1, 0.5, 1, 2, and 5. I am going to get things out for y. I will. I am going to now show you how to use this on your calculator, because these numbers are not going to be the exact same numbers I got out for base 10. Now, at first, you might go, oh man, I'm totally confused. You lost me with this base thing. Here's why I had to break this into 3 videos. To actually graph one of these or do the problem, it's pretty easy. To understand what's going on, that's going to take us a couple weeks. This unit is a 2-week unit. We are not going to get everything done in 1 week. So, ready? I want to plug in log of 0.1. So I'm just punching in log 0.1. But I have to trick my calculator into thinking it's base 7. So I then hit my divide key, divided by, and then I punch in log of 7. Look at my display. So I want to know what the log of 0.1 is. But to convince my calculator that it's no longer in base 10, that it's in base 7, I divide by log of 7. I'll get an answer, and I will round that thing off to the nearest tenth. So I'm going to get negative 1.2. And I'm going to write that down, negative 1.2. Let's plug in 0.5. So I'm going to say log of 0.5. But I don't want my calculator to give me the wrong result. I'm going to say divided by, whoop, there it is, the log of 7. There's my display. What did I do? Now I'm going to plug in log of 0.5 divided by log 7. What's it going to give me? Some other ugly decimal. But I'm going to round it off to the nearest tenth. And I'm going to call the answer negative 0.4. And I don't even want to punch this one in, because the log of 1, no matter what I do, log of 1 is going to be 0. So if I divide it by the log of 7, it's still 0. You take 0, divide it by anything you want, you still got 0. So this answer is always the same. And then take a look at, I told you there's a little pattern with the numbers I like to use. So I'm going to do log of 2 divided by log of 7. And check it out. I'm going to get, oh, do you see that? Isn't that magical? How pretty is that? So I'm just going to go, oh, 0.4. So basically, if I know this answer, I'm going to know this answer. Let's do log of 5. So I go log 5 divided by log 7. And I get 0.8-ish. So I'm going to say 0.827. That's 0.8. Let's take a look at what would happen if I graph this. If I graph this, I only need to plug in. 5 is the biggest number I plug in. And look, when I plugged in 0.1, I got out negative 1.2, so I'm down here. When I plugged in 0.5, I got out negative 0.4, so I'm about right there. 1 gave me 0. It did. 2 gave me regular 0.4, so let's... And then 5 gave me 0.8. So when I connect the dots, remember, asymptote down below, and then it's a slow climbing curve. This goes down forever. So let me ask you, here was my first graph. Here's my second graph. They almost look the same. Well, look at how close the output values are for these. When I plugged in 0.1 here, I got out negative 1.2. Here I got negative 1. Look at how close these answers are when you round them off. They're super close. So guess what? The pictures are super close. It's true. Logarithmic functions all have the same type of look to them. They all have the same type of vibe. So here's the thing. I'm going to go back to my calculator because I want to show you how to check your work on this one. I am going to say, I'm going to clear this one out, just get rid of it. But I know to graph this on my calculator, I'd have to enter it like this. Y equals log x divided by log 7. Whoops, I'm running out of room there. That's what I'll have to enter in to get that thing to draw it. So I say log x, close the parenthesis, divided by log 7, close the parenthesis. And now if I hit graph, here's my picture. Yep, that's my picture. Hey, it looks just like the last one. Well, let's compare them. I'm going to do y equals log regular x. So y equals log x, here it is. And this will be in red. So you'll see the difference is super duper subtle. It's really subtle. Look at that. One is just slightly below the other. I can't tell. Well, I'm going to zoom box. Hey, what the heck? I haven't done this in a while. I could zoom box this stuff. And remember, to draw a zoom box, you just have to have some kind of spot that you want to start with. And I'm going to go down here. I'm going to draw this nice skinny box. And let's take a look. Now let's compare these two. There's the log base 7 graph. Log base 7. Here comes log base 10. Here it comes. See, there's just a slight difference in the two graphs. Super tiny difference in those graphs, but they're different. Now, I'm going to turn this off and get this out of my way for a second. Not all log graphs do this. I'm going to show you what happens when I have this type of base. Let's just look at this type of base. So here we go. I am going to plug in X information. I am going to get out Y information. My plug-in numbers are going to be the same every time, 0.1, 0.5, 1, 2, and 5. That's my input. I am going to have to trick my calculator into thinking it's base 0.2. So when I plug it in, I'm going to say log of whatever number they want me to do divided by log of 0.2. Hey, look at my coordinate system. I did this kind of on the other assignment too. I know that I 1, 2, 3, 4, 5. I only have 5 inputs. Nothing on this side, so I didn't draw a bunch of junk over here. I only need like 1 or 2 dashes up here and 1 or 2 dashes down here. That's how my graphs have worked out. What the heck? I already know this is going to be an asymptote. So what I'm trying to get at is this. In the first lesson about exponential functions, our graphs all look like this. Watch, I'm going to turn it. Oh, look at that. Our graphs all look like that, right? Or like, huh? And with logarithms, all our graphs are going to do this, like, oh. And then this one you're going to see goes like this. It comes down. Instead of going up, it's going down. Why? Because this number here is less than 1. That's why. Remember, there's a big overview video coming your way. But until then, let's just practice doing the basics. I'm going to clear all this junk out. Clear. And I am going to say, I want to know the log of 0.1, but I'm going to divide it by log of 0.2. Why? Because I want to trick my calculator. I want to trick my calculator into thinking it is base 0.2. And that's as easy as it is. I hit equals, I get an answer, I round the answer off, I say 1.4, thank you very much. I go again. Let's do log of 0.5 divided by log of 0.2. And I get 0.43, so I'm going to round that thing to the nearest tenth. This guy's 0. I don't even want to bother. Anytime I take the log of 1, I get 0. It's always the same. And can you guess what this answer is going to be? What's the guess here? I think it's going to be negative 0.4 because I like the fact that I noticed a pattern here. But let's double check it. What is the log of 2 divided by the log of 0.2? See, there it is. There's my guy. It's the same number. It's just reverse the sign. And then last but not least, log of 5 divided by log of 0.2. You ready for this? This is going to be negative 1. Hey, guess what? Sometimes you get really weird decimals for logs. Sometimes you get super weird decimals. And sometimes you don't. Sometimes you get regular numbers for logs. It will happen. You'll be working on a problem and go, I got 3. And then there's other times where I got 0.4306765, etc., right? But here we go. We have enough information to draw a graph. When I plugged in 0.1, I got out 1.4, so I was up here. When I plugged in 0.5, half of the way, I got out 0.4. 1 gave me 0. When I plugged in 2, I got out negative 0.4. And then when I plugged in 5, I got out negative 1. Now this is what happens when you have a base number that's less than 1. You get this look. You get the log, but instead of go... Oop, I missed that dot. Oop, make that dot bigger. There. And this goes up forever. It's asymptotic. So hey, guess what? Just like we had with exponential stuff. Exponential stuff, we had growth and decay. Logarithmic stuff kind of has its own feel to it. This is a swoop down. Now notice, my first example was base 10. Base 10, that number is bigger than 1. It goes like this. That was base 7. 7 is bigger than 1. It goes like this. 0.2, come on. 0.2, less than 1, swoops down. So, I just want to make sure that you understand that you can graph these guys easy, but you might be like, I don't know why I'm changing this base. I don't really know what that means. Well, for now, what do I want you to know about it? I want you to know that when this number changes, it means this graph is going to look different. Even though they all look very similar to each other, they are different. So let's talk about this one. I want to get an idea what this guy's going to do. I want to sketch this graph. But you know what? I know for sure I'm still going to just plug in the same input. So I'm going to use 0.1, 0.5, 1, 2, and 5. Those are my x's. Whenever I take the log of 1, I get 0. I do. So I know that guy is already there automatically. Totally going to get that. But I want to trick my calculator into being base 1/2. And you know what? Since it's 1/2, I could punch it in as 0.5 on my calculator too if I wanted. But here's the dealio. This is the first time I've done this to you guys. That's a scalar. So guess what? The X inputs are never going to change. When you graph a logarithmic function for me, you can always use those because they're always going to give you enough information to graph it. But guess what? This is going to affect the scale on the y-axis. So guess, I'm just going to go for it right now. I'm going to call that 20. I'm going to call that 40. I'm going to call that negative 20. I'm going to call that negative 40. And that's why these two lessons, exponentials and logarithms, kind of go hand in hand. They're different input, different feel, different weirdness. But you know what? There's a lot of similar things that they do. So I am now going to grab my calculator, and I am going to clear all this out, and I am going to say 20. So I'm going to punch in the number 20, and then I'm going to go log 0.1, close the parenthesis. But I have to trick my calculator into being base 1/2, so I'm going to say log of 0.5. So look at what I had to input into my calculator. 20 is the scalar. Log 0.1 divided by log 0.5. Notice I close my parentheses. I don't want it to mess me up. And I hit equals or enter. And I get 66.4, blah, blah, blah. I'm going to call it 66.4. I'm going to punch in log. Wait, sorry, not log 20. Log 0.5. divided by log 0.5. Now, speak of the devil, this answer's 20. Yeah, it is. You can get regular numbers for logs. I told you could. Wow, sometimes I get weird decimals. Sometimes I do not get weird decimals. Yeah, there's a pattern. We'll talk about it. This is the first lesson. We're just trying to get used to our calculator and how to punch in log numbers to it. So here we go. 20 log of 2 divided by log 0.5. And guess what what am I going to get right here? I'm going to get out negative 20. You didn't plug in the 1. I know, because I always get out 0. Oh, but look at that. I got another regular number. There is a pattern there to be found. We will talk about it eventually. Now let's do the last one. So I'm going to do 20 log of 5 divided by log of 0.5. And what's my answer? Negative 46.4. Okay, I'll buy that. Negative 46.4. But you know what? I already scaled my graph, because of the scalar. And when I plugged in 0.1, I got out 66.4. So 0.1 input, I get out like 66.4. So I'd be up here, right? And then 0.5, I got out 20. When I plugged in 1, I got out 0. Here I got a negative 20. And then I got a negative 46 way over here. And let's connect these dots. Remember, it's going to go up forever. Oh, come on. I'm trying. Oh, that was pretty good right there. Okay, there's not supposed to be a break. And guess what? There's my asymptote. It totally is asymptotic there. Oh, yes. And it swings down. And if I wanted to check my graph on the calculator, I could go back to y equals, clear this junk out, and I could say I want to graph 20 log x, but I'd have to trick it into base 1/2. So I'd say divided by log of 0.5 or log 1/2. But when I hit graph, wait a minute, I forgot to zoom standard, I think. Or wait a minute, let's see, my window is kind of messed up. Remember, when I'm graphing, I can change the window that I'm looking at. And this case, I don't need anything on the negative side of the x-axis at all. And I only plug in 1, 2, 3, 4, 5 at the biggest. I never changed the scale on my x, but you know what? My graph went as low as 46 and as high as 66. So I'm just going to go, hey, you know what, Y-man? I'm going to make you say negative 50. And y max, I'm going to make you say positive 60. What the heck? I'm going to make every dash on the y worth 20. Every dash worth 20, because that's the scalar that I want to use. And I hit graph. Check it out. Oh man, is that looking like my graph here? What? How beautiful is that? That is fresh in a deaf way. So, guys, graphing things, check it with your calculator, get used to what you're doing here, and if you get stuck or you get confused about anything your calculator is trying to tell you, ask me in class so I can help you through it. Because once again, hey, guess what? We're grabbing a graphing calculator. We're taking a look at some pictures here. All right. Turn off. So, here's my question to you. I'd like you to pause this lesson right now and just see if you could do this one. I want you to graph y equals 50. Would be the scalar 50 log base 5.1 of x. What would you plug in for x's then? You would use the same stuff you always do, 0.1, 0.5, 125. In fact, here that's a free space. It's going to be 0. It always is. And then if you do it right, these two match, right? And then, so here we go. Let's see if you can sketch this graph. Pause the video and then do it, and then hit play and check your answer. So here we go. I'm going to say 50 log 0.1 divided by log 5.1, because I have to trick my calculator into that base. I get negative 70.7 if I round it off. I'm going to do 50 times the log of 0.5 divided by log of 5.1, because I want to trick my calculator into that base. I get negative 21.3. You know what? This one's going to be 21.3 then. It should be, because I know log of 1 is 0. Well, what the heck? Let's just verify it. Let's go, you know what? There's a reason why he wants me to use these numbers every time, because they do kind of save me some time if I do it correctly. And they're the exact same number, 21.3. How about the last one? So we go 50 log of 5 divided by log of 5.1. And we get what? 49.4-ish. So we'll call it 49.4. And I plug in the same x values every time. I have an asymptote right here. I'm going to count by 50s because that's the scalar. So let's plot some dots. When I plugged in 0.1, I got out negative 70.7. So right about there. I'm guesstimating. I plug in 0.5 for x, I get out negative 21.3. Here, I plug in 1, I get out 0. It's a free spot. I get it the same every time. 2 gives me 21.3. 5 gives me 49.4, so I'm pretty much at 50. And I sketch the graph. And once again, all logarithmic graphs have the same type of feel to them. They have the same type of vibe. Just like all of my exponential graphs had a certain vibe. So look, that one is if the base value is bigger than 1. And remember, when there's base values that are smaller than 1, it does this. So when you graph a log, all your answers either do this thing or this thing. Kind of like when you graph an exponential, all your answers did this thing or they did this thing, okay? There is a method to what's happening, etc., and all that. But once again, if you want to check your work, there it is. If I were going to check it on the calculator, I would make sure that my window went as high as 100 and as low as negative 100, so I could get my graph to look just like this. But my x values, 1, 2, 3, 4, 5 is the biggest number I plugged in. X max is 5, So, guys, that's my graphing logs video. And we'll talk about what that base thing is, what's up with that base, right? Because when you talk about logs, you're going to be all about that base, right? All about that base. No trouble. All right, had to get that bad joke in there, and now I feel better about myself. Okay, the last video is coming up for this first unit lesson. So hang in there. One away from the actual practice problems. Bye-bye.